Today when we look at sums and differences of radicals, here's what I want you to think. Remember yesterday when we simplified something like this? Let's say we have that. Square root of 75x to the third. We break it into 25x squared, because those are perfect squares. And over here I'd put a 3x. Okay, again, why do I do that? So that the left-hand side has a perfect square, right? And now when I reduce that, it simply becomes 5, and well, this is going to be an absolute value of x, times root 3x. What did I say yesterday to think of this as? A coefficient. Okay, see this 5, absolute value x? Think of that as a coefficient. Think of this entire radical as a variable like y. In your mind, think of it that way. So here's what I would see. I would see, well, this is like a coefficient, 5, and this is like a y. So think of it in your mind as whatever this is a coefficient, and whatever this is as the variable term. So far, so good? Just think of it. You don't have to write it, but think of it that way. All right, let's take a look at our first. And that's what I'm saying here, sorry, in the first slide. I want to give you the example. So again, treat them like variables. Simplify them first, then combine like terms or like radicals the same way. So let's look at an example to see what I'm here. Example A in number 1 says to simplify. What do I get when I simplify radical 48? We did this one yesterday. What does 48 break up into?
16 and 3.
Yeah, 16 and 3. What about 75, Ida? Keep going.
27.
And what do you notice? What do you have common in both of these, Ida? Radical 3. And you think of that as like a variable. So we end up getting, ready, 4 root 3 plus 5 root 3, which is just how many root 3's? 9 root 3's. Think of them like variables. Wouldn't this be 4x plus 5x? And 4x plus 5x would be 9x. So think of the root 3 as an x, as a variable term. Think of the numbers in front as the coefficient. If you need to write that down at the top. Or write it in red. Write it like this. Here, do this. Think of this as 4x plus 5x. Put a line there so you can see what I'm saying. Think of these as 4x and 5x, and they would become 9x really. So instead of 9x, you really have 9 radical 3. Does that make sense what I'm saying? You're going to continue to do this for all these. No matter what problem you have, when you're adding or subtracting, you're going to treat them like terms. Okay, we'll call them like radicals. How about part B? Part B is only difficult because they're cube roots now, right? Because they're cube roots, but it's the same process. So tell me, please, only the first part, the cube root of 16. What do I break that into? Yeah, 8 and 2. So this becomes 5. Cube root of 8. Cube root of 2. Why did you choose 8 and 2, Dave?
Because you can also use 2.
Yeah, but why did you choose it, Dave? Forget this. That's the real reason. Okay, that's the reason you have to. Because if you can't pull out a perfect cube, then you're not going to be able to do anything with it, right? So this becomes the real reason. Then this happens to correlate. And you'll see the correlation. That's good that you notice that. But the reason you pick 8 and 2 is because 8 is a perfect cube. 8 is a perfect cube, right? What's 8 the perfect cube of?
2.
Yeah, because 2 times 2 times 2 is 8. So this cube root of 8 happens to just be a 2. So this becomes 5 times 2. So I could already write this as 5 times 2 times the cube root of 2, or 10 cube root of 2. Okay, that's what the first part becomes. How about the second part? Somebody else, give me the second part. 54. What do I break it into? Cube root?
The cube root of 2 and the cube root of 27.
Yeah, perfect. And I'm going to always write the perfect cube first. So let's say it that way also. Just to remind me that it's like a coefficient now. Now do you see why I did that?
Yeah.
Remember the other day I said to put the perfect thing first? So when you reduce it, now you have a number in the front. What is the cube root of 27? 3. Liam, why? Exactly. 3 times 3 times 3 is 27. So this becomes 3 cube root of 2. So now I'm adding 10 cube root of 2 and 3 cube root of 2. How many, Natalie, cube roots of 2 do we have? Oh, sorry, I'm subtracting them. So Natalie, how many do we have still, either way?
7.
Yeah, 7 now. Sorry, thank you. Subtract. So our answer, I'll put at the top up here, is going to be 7 cube root of 2. Thank you for reminding me that we're subtracting. Okay, does it make sense? How about part C? How about part C? It's going to be a bit tougher. And we can't add those until we get common radicals. And these are not common, so please don't try and add the fractions. You can't do it. You can't add these together. Because remember, these have to be the same. Remember we got the root 2's there, or the cube roots of 2, then we added them. We need to get the same thing under here before we can do anything. Ida, give me a starting point for this one.
Can you split the 50 into 25 plus 2?
Okay, good. It was 50 over 3 plus,
2.
and they were both square roots, right? So yeah, let's break the 50 into 25 and 2. I absolutely agree. Okay, I'm going to have to rationalize anyway. So I can add or rationalize first, it doesn't matter. But that's kind of what we're thinking about. This becomes 25 times 2 up top, the 3 is in the bottom. This 2 and 3 are really separate from one another. Making the top 5 root 2 over 3 plus root 2 over 3, root 3, sorry. So at this point, you have common denominator, don't you? So you technically could add the numerators. Remember with fractions, if I have 1/3 plus 1/3, it is what? 2/3. Same thing here. I've got 5 root 2 over root 3 plus 1 root 2 over root 3. How many root 2's does that give me over root 3? How many? 6. This is a 5 plus there's really a 1 in front of here. This is like 5x plus 1x. And they're both over root 3. So root 3 is the common denominator right now. So I could start by writing that out. And then add the numerators like you would add any other fractions. Okay, so again, if it were 5x plus x, it would be 6x. So it's really 6 root 2. Common denominator, you just rewrite it. This is why those laws you learn in middle school are so important. So if you struggled on that stuff, that's the stuff you need to work on really before you can get on to this. Okay, so please make sure that you work on that stuff if need be. Come ask me or watch some videos on YouTube on how to add fractions to make sure you get common denominators.
So you can't add fractions until you make until they're like even, like radical.
Or they have common denominators, right? Look back up here. It looks like they have the same denominator, but once we write it like this, now they have the same denominator. Look at this part, right? It's tempting to want to add this and make it 52 over 3. That's the most common mistake. But then you'd be adding inside of radicals. Here, when they're separate now they're not inside of the radicals. These are separate from one another. So either you could reduce them first, or you could find the common denominator of each of them. Okay? But this is very different. This 5 root 2, I'm adding that to root 2. I'm not adding these numbers together. See how that becomes 52? Do you see 52 anywhere? No. Okay, so it'd be voting your laws.
Okay, so when does, radical, what's it called, something with the denominator, when you multiply by 3?
That's what we're going to do right now to rationalize. We're not done.
Oh, okay.
Okay, so let's rationalize. That's all right. So what would you do, Tori, man?
So you would multiply the top and bottom by 3, root 3.
Thank you.
Yeah, sorry.
Making the bottom just,
3.
and the top 6 root.
6.
Yeah. Which reduces, technically, to 2 root 6. What's 6 over 3?
Oh, right, because it would be 6x.
Think of this as 6x over 3, right? If this were 6x over 3, the 6 and the 3 would cancel, making it just 2x. So now it's just 2 root 6. It's just 2 root 6. Tough problem, for sure, but it's not impossible. So when you're on your homework and you say, oh, I didn't know what to do, you need to try stuff out. You need to go through the problem and see what you get. Okay? How do I check that I'm right? How do I check that I'm right? Even if it's an even problem, you can check. How do I do it? Come on, people. Think outside the box. What was the original statement? That was the original statement up there, right? Can't you type that in your calculator and get a decimal for both of those and add them together? And then can't you type your answer, 2 root 6 in the calculator and get a decimal and see that they're the same? Go do that right now, please. When you're on the SAT and you want to check that it's right, you can go ahead and do this. You can go ahead and type in each choice if you forget how to do this. If it's multiple choice, obviously. Okay, but there's a good chance there'll be a variable in it, and then you would have trouble. You can't really do it with variables. Go ahead and try this though. Type in the original, square root, it'll open up a parentheses, put 50 over 3, close parentheses, hit enter, plus the square root of 2/3, get a number, and then check the bottom answer here that we got, and see if they're the same or not. Again, you have the original on your paper. You have the original on your paper, and you should have the 2 radical 6 at the bottom. Check that you get the same answer, please.
Got same answer.
Everybody verify. Don't just take Worth's advice. Sorry, Worth. I believe you, but I want everyone to do it.
Worth it, worth it.
Tori, you're not funny. You never
That was pretty funny, but it was corny. It was good.
It's your holiday.
It's a joke I would probably make. After the fact, I would make the same joke.
Come on. I'll give you my first.
Howard Duck? I was looking at Howard.
Yeah, I thought it was charging last night, and then I go to get it this morning at 1%.
How was it not charging?
I don't know, I think like 4 hours so.
Let's move on to the next example. Is that all right? Yeah, we all got the right answer? We checked it? All right. Here we go, here we go. Let's do this. I know. And it begins. And it begins. Relax. You can all do this.
It looks fun.
Everybody says, but it's really not hard. All right. Come on, quiet. Now, can I get a word of advice for the first one? Who would recommend a beginning point for part A?
Okay.
Of course.
You can find maybe you can simplify 5 radical 48.
Okay, break 48 into? We just did it. We just did it.
16 and 3.
Thank you. We just did it, Tori. Come on. Next. I have to do something there. Think of these with your laws of math. It looks like what property is illustrated? Distributive. So distribute. Now, this is where it gets a little tricky. Things on the outside multiply and things on the inside multiply. So let's do the 4 root 6 times the 3 root 2 first. Okay, and it's negative, right? What's negative 4 times the 3? Here, look up at the board, please. Negative 4 times this 3 right here gives me negative
12.
Okay, then I have root 6 times root 2 giving me root 12 also. Next, negative 4 times negative 5 is positive 20. And root 6 times root 3 is root 18. Do you see how this is not difficult, folks? Right away everybody says, it's not difficult. Break it down further. Notice, what root is in the first one that's going to be left behind? So what do you think is going to be in these ones? Or maybe? Maybe, right? We'll try. So can we do it here? 4 times 3, right? But the other one doesn't work, and that's all right. And don't jump to the gun and say 6 and 3. 6 is not a perfect square. What do you break 18 into? Yeah. Because you see the root 3, so you all want to say 6 and 3.
9.
Root. Yeah. 9 is the perfect square. So this is not going to be a like term. It's okay. It's like having x's and y's. You just can't add them at the end. But we can add the first two together if we simplify further. Let's keep going. What's 12 times, this is really a 2 here.
24.
Thank you. I'm simplifying the root 4 to give me a 2 right there. Simplify the root 9 to make that a 3. 20 times 3 is 60. So this is like having, ready? Here we go. 20x minus 24x plus 60y. Do you see the difference there? The root 2 and the root 3 are like having two different variables. They're not like variables, or they're not like radicals. So the 60 root 2 is not going to be simplified any further. We leave it alone. That's like having 60y at the end. But what's 20x minus 24x? Negative 4x, so it's negative 4 root 3.
Would you say root 3 or radical 3? Because I learned this last
Oh,
year.
either way. That's fine. But what happens when you get like a second root? You wouldn't say second radical. Radical is the symbol. The term is actually root. So if you have like a third root, you say third root or cube root. All right. And notice I'm dropping the word square, just like you would drop the 2. You know, you wouldn't say second root. You would say square root or just root. The index is kind of not there. How about part B? Yeah, Dave.
Can you scroll up to start T?
First one.
Oh, thank you.
Just give me a starting point.
You can simplify both.
We can simplify both of them. But now they're variables. So we need to look for things that are x to an even power. But those are both odd powers. X to the third is an odd. X to the fifth is an odd. We want even powers because that can be divided by the index of 2. So what should I break x to the third into?
X squared.
Yeah, so let's start with that. What should I break x to the fifth into?
X to the fourth X.
Yeah. And notice the root x that's left behind in both terms. So these will be like radicals here. What is the square root of x squared? Yeah, now we're going to end up, it's really absolute value of x, right? We're going to multiplying by 4x here in the front.
What it becomes X squared. So
4x squared.
Yeah, and that's what I'm going to, but just to show where it comes from, okay? But this is going to become 4x squared.
Hey.
Can we erase the
Okay.
part of getting competitive?
I put a line. Just don't look at it. What's the square root of x to the fourth? The square root of x to the fourth, Austin?
X squared.
X squared. Because x squared times x squared is x to the fourth. Or what's the index? What's the index that's not here? And what's 4 divided by 2? That's why it's also x squared there. So we have 4x squared minus 1x squared with the radical x's tacked on. So again, think of these x's as y's or other variables. Here, Summers, does this make it better? Think of it this way, okay? So think of it this way. How many x squareds would you end up having there? 4x squared y minus 1x squared y is 3x squared y. But it's not y, it's root x. I know, but it's the same thing. You need to trick your mind into it. Look here. Stop. Look up here. At this point in time, this is the same thing. I'm replacing the radical x with a y so you can see that these are like radicals or like terms. If you have 4x squared y minus, there's a 1 here, 1x squared y. It's 3x squared y. But the y was really the radical x. So I'm just thinking of it this way. This is not really in the problem here. I'm just thinking of that. So you could go from here right down to here if you understand what's going on. If you're having trouble, just replace whatever the radical is, the common radical, with a variable of choice and then go through the operation. I'm not going to replace it with x because that wouldn't make sense because I already have x. That's why I chose y to think about it that way. Okay? But again, go back up to here. This is like 4 minus 1, which is 3. I carry everything else down. Okay, I carry everything else down. Another way to think about it. Think of this as 4 parentheses x squared root x minus 1. Oops, any more room? Minus 1 x squared root x. Does that make it easier, actually? Think of this part right here. It's putting your laws of associative laws of multiplication say that you can introduce a parenthesis anywhere if you have grouping, right? So if I introduce a parenthesis where my fingers are right here, and then another set of parentheses around here, isn't there really a 1 in front of here? So that's what it would look like. And then isn't this just the same thing? Aren't those identical? So this is like 4y minus 1y, which is 3y. That's the same answer as what you had down here. It would become 3 parentheses x squared root x, which is the same answer as what we have down here. Okay, this is not distributive property. There is no plus sign here. Please don't distribute this afterward to both. This is not distributive. This is associative property multiplication, which tells me I can take this big parentheses and just put it around the whole thing. And that's where this answer comes into play. Okay, so pick any root. It's up to you, not root as in radical, any method. Because it is up to you to decide which way you want to take the problem. Okay? In the video, when I record, I usually pick one way to do it, but it doesn't mean you have to choose that way. That's why I'm trying to give you alternate possibilities here. Dave,
The next one, you're the rationalize the denominator.
let's take a look. Yeah, that would probably help. That would probably help, but we're going to run out of time in about a minute, so I'll record this and I'll leave it to you to watch.